Lesson 15.1, Task 1. Identify monomials. A monomial is a number, a variable, or a product of a number and variable with whole number exponents. A monomial is always an expression with a single term. The general form of a monomial in one variable is ax to the nth power, where a is a real number, x is a variable, and n is a whole number. All right, so here's some examples of monomials, okay? So you got a coefficient, a variable, and an exponent. All right, so examples here, square root of 3x. Your coefficient is the number in front of x, so your coefficient is square root of 3. The degree is the exponent. When there's no exponent, it's assumed to be a 1, so it's degree 1. And then this one's xy cubed, so the x would have an exponent of 1, and 1 and 3 make degree 4. Since there's no number in front of here, again, the number is assumed, or the coefficient is assumed to be a 1. All right, so you got negative 2x to the third power. Negative 2 is your coefficient, and 3 is your degree, okay? 16x to the fourth, yz squared. 16, the number, is your coefficient, and your degree of the monomial is the sum of your exponents. So 4, the y has an exponent of 1, so 4 plus 1 is 5. 5 plus 2 is 7, so the degree would be 7. So these are all examples of monomials. So you can see that they're all one term. And it's a product of a number and variable with whole number exponents. So whole number exponents, that's important to remember. All right, so it says when a monomial consists of only a number, the monomial is called a constant. When a monomial consists of a number and at least one variable, the number in the monomial is called a coefficient. A monomial can have multiple variables as long as the exponent of each variable is a whole number. The degree of a monomial is the sum of the exponents of the variables in the monomial. The degree of a non-zero constant is 0, and the constant 0 does not have a degree. The first table shows some examples of monomials and identifies the coefficient and the degree of each monomial. A monomial cannot have multiple terms, variables in the denominator, or a negative or fractional exponents. So a monomial cannot have multiple terms, variables in the denominator, or negative or fractional exponents. Examples of expressions that are not monomials and the reasons why they are not monomials are shown in the second table. All right, so non-examples. So this one's not a monomial because it has two terms. X minus 2 has two terms, so it's not a monomial. Mono means 1. 4 over y, this one has a variable in the denominator, so it's not a monomial. X to the negative third power, because it's a negative exponent, that can be rewritten as 1 over x to the third, which moves the variable to the denominator. So therefore, negative exponents are not considered monomials either. And then fractional exponents. So y to the 1/3 power, this is 1/3 is a fraction, so that is not a monomial as well. All right, match the description to the monomial. All right, so a monomial with only a number. I don't know why I jumped to the second one first, but I did. A monomial with only a variable. And the monomial with a coefficient and a variable would be this one. All right, complete the statements that correctly compare 5x to the third and 5x squared. So the coefficients are the same. They both have a coefficient of 5. The variables are both x, so the variables are the same as well. And the degrees are different. 3 and 2 are different, so the degrees are different. All right, so complete the statement about the expression ax to the 0 when a is a constant and x is not equal to 0. So the value of ax to the 0 is Well, whatever a is, that's what it would be, because x to the 0, remember anything to the 0 power equals 1, and 1 times a is just a. The degree of this monomial is 0. Remember, the degree comes from the exponent or the sum of exponents if there's a product of variables that have exponents. All right, so which statement explains why the expression negative 4xy to the negative 3, 0.5 plus square root of 2x, and 3 over x squared are not monomials? Select all that apply. Well, this one has a negative exponent. So the negative exponent is the first one. This one is plus 0.5 plus this term. So that's 2 terms. So monomial is 1 term. So this one has 2 terms. And then this one has a variable in the denominator. And if you go back up top and look at the definition, you will see all of those reasons as well. All right, that's all for task 1. If you have any questions, let me know. Lesson 15.1, Task 2. Multiply monomials in one variable. You can use algebra tiles to model multiplying some simple monomials in one variable. To find more complicated products of monomials, algebraic properties can be used. A key for interpreting algebra tiles is shown. All right, so if you have the square tile and it has a plus in it, that represents x squared. The red square represents negative x squared. The yellow rectangular shape represents x, and the negative, or the red rectangular shape, represents negative x. So this is your key for your algebra tiles. So it says the algebra tile diagram shown represents the product of 2 monomials. So this would be 2x times 3x. So you can see these represent x. So 2x times 3x, and then x times x represents x squared. So that's where the x squared comes in, okay? All right, so it says, what are the 2 monomials whose product is modeled by the algebra tile diagram? So again, we've got 1, 2, 3 x's on the side and 2 x's on the top. Choose the correct words to explain how you identified each monomial. Look at the tiles along the top and left side of the model. Those parts of the model show yellow rectangular plus tiles. So you can see the rectangular tiles on the left side and the top. Each of those tiles represents an x, so that it is a variable part of the monomial. Count up the number of tiles in each location. The number of tiles is the coefficient of the monomial. So remember, the coefficient is the number in front of the variable. So 2x and 3x, so the 2 and the 3 are the coefficients. All right, so how does the algebra tile diagram show the product of 2 monomials? Choose the words to correctly complete the statement. The product is modeled by the, 3 x tiles to the left and below the x tiles that represent the 2 monomial factors. Let's see. So the product is modeled by the 3x tiles to the left. Oh, wait a minute. The product is what's in the middle. All right, so the product is represented by this part here. So let's see. So that's 6 by the 6x squared tiles to the left of the and below the x tiles that represent the two monomial tiles. All right, so I think this is correct now. So the product, that means your result. So what it wants is to know what is 2x times 3x. So that would be 6x squared. So that's going to be our 6x squareds. And that shows up. Well, this is the left, this is the right, so this one should be the right side. So this is 6, got my left and right mixed up. So this is 6x squared to the right side and below. All right, so again, I pointed to the right spot, but I put the wrong answer here. So this is the left side and this is the right side. All right, so it says, what is the simplest product? So it'd be 6x squared. And then it says, what are two monomials whose product is modeled by the algebra tile diagram below? All right, so we've got 4 x's and negative 2 x's. So we've got 4x and negative 2x. So the negatives, remember, those are still rectangular shapes, so they're still x's, but they're negative, and then 4 positive x's. What is the simplified product? Well, 4 times negative 2 would be negative 8. Show how you could use properties of exponents to find the product modeled in the first tile diagram. Match each step to its justification. All right, so this is rearranged, so that would be commutative and associative property. All right, and then this would be definition of a power. So if you have a x, you can rewrite that as x to the first power, okay? And then here, same base, you add exponents. That would be the product of powers. And then this would just be the simplified exponent. All right, choose the correct expression to show how you can use properties of exponents to find the product modeled in the second tile diagram. All right, so we've got negative 2x and 4x. So we can rearrange that to do negative 2 times 4 and x times x. That's commutative and associative property. Then we can, definition of first power, we can write this with ones. So negative 8. And that is a product, so it continues to be a product. And so we have negative 8, product of powers. That means we add our exponents together, and then we simplify, so negative 8x squared. All right, can you use algebra tiles to find the product of 3x times 4x squared? Why or why not? All right, so x times x squared is going to be x cubed. So that's a three-dimensional shape. So I'm going to say no. Why is it no? No, because there are no algebra tiles that represent the product of x times x squared. No, because there are no tiles to represent the number 3 and 4. So this would be the best choice here. When you multiply x times x squared, you get x cubed. And even though you can multiply that, we usually don't represent those in tiles. All right, choose the correct number and expressions to find the product. So again, they rearranged this, and we got x times x squared. And here we've got 3 times 4, which is 12. And then here we go 12 and x to the third. Oh, well, they add the exponents. And then x to the, or 12x to the third power. All right, match each step of the calculation that you can to complete the justification. All right, so those are the same justifications as before. And the last example here, let's see if I can get through it real quick. A times B, multiply here.